Good. So where are we at in our progress towards training our neural net? Well, first of all, we've defined what it means to take a forward pass through the data, and that is you start with an X, and then you compute the pre-state on the first layer and the state on the first layer, which are both X. Then you move to layer 2, and in layer 2 you take the pre-state to be W times the X plus B1, and then you apply the activation function to that, and then you go to the next pre-state, and then the next state, and then you go to the next pre-state and the next state, and you keep doing that. Of course, we just have a 3-layer net, so we're really only doing one layer of activation. Um, okay, so then we talked about going backwards, and going backwards, the idea is we want to compute these deltas. And so the deltas are being used directly to measure how much we should change our weights. And so we got the matrix version of that. Excuse me. Okay, so we now have defined everything we need for training, right? We know how to change our weights. So what am I doing here? Well, what we need to do is still prove that what we're doing is gradient descent. And so that's what I hope to do right now. So we want the gradient of the error. All right. So our error function is, well, the full error function is taking the sum over all p data points, and this is just our sum of squares error. I put the 1/2 here because the 2 and the 1/2 would cancel nicely, so I don't have to worry about that. Okay, and so what we want to do is we need to compute the partial derivative of the error with respect to one of our training parameters. So let's just go ahead and define that. Just to make it consistent with the notes, we'll take w sub mn and script L. Okay, so where does this parameter sit in our neural net? Well, it connects two nodes between layer L and layer L minus 1, and this is node N, and this is node N, and this is node M. It looks like MM. Okay, and so in terms of the algebra, right, on layer L, we have that SML, the state on the mth node of layer L is just going to be sigma of the pre-state of node M on layer L. And now when I'm computing the pre-state on this, there are other incoming cells here, but I'm really only interested in where does this weight come in. Well, so PML is going to be a bunch of weights times the states, but the only one I'm interested in is W, M, and L. And then what's the state value going to be? That's Sn on L minus 1, right? And then we're going to have plus a bunch of other stuff that I don't care about. Okay. Good. I think we're ready to compute our partial derivative now. So I'm going to take the partial derivative of the error with respect to W, M, and L, and I'm going to rewrite it as a product of three things. Partial derivative of the error with respect to SML, because that's where the parameter comes into play. And then we'll multiply that because SML depends on PML, the pre-state. Oops. And then the pre-state depends on W, M, and L. Good. All right, so we've actually already know how to compute some of these. This part of the error, you can just see over here. What's the partial derivative of this with respect to W, M, and L? You see that it's just S and L minus 1. Almost messed that up. What's the partial derivative of SLM with respect to PML, and that's just going to be sigma prime. And we've already computed those on each node as well, right? So the only thing that I need to figure out is how to compute the partial of the error with respect to the state. Good. So the idea is we're going to take this from our previous video and we're going to write this recursively. Going backwards. Okay. So on the output layer, my headphones are coming off. Sorry about that. On the output layer, we have y1 coming out, ym. Remember that these are the s values, right? Okay, so if I'm taking the partial derivative of e with respect to, I shouldn't have used m. Sorry about that. The m here does not necessarily equal the m here. This m here is fixed, right? That's the dimension of your output. But this is just a generic m, okay? So the derivative here is going to be the same thing. Oops, that's the output layer. That's just the same thing as the error with respect to m. And so remember that the error here is ti minus yi. I should write that somewhere else. Okay, sorry about that. I squeezed my error function in up here. So what is the error with respect to the nth variable here? Well, it's just going to be 2 times tm minus ym times minus 1, right? And so, yeah, so on the outer layer here, we can construct all of these at once, right? By just taking tm minus ym times minus 1. Notice that these are almost the same thing. Oops, sorry about that. This is t1 minus y1 times minus 1. Tm minus, so if on the nth one I should say it's this value in particular, right? But we can go ahead and compute them all for the output layer. Good. Alright, and again, like I was saying, this looks very familiar. It's actually minus the delta on the output layer. Okay, so if you've already got your deltas, then you already know what these are. These are going to be minus delta on the output layer. And so this negative sign is what's going to allow us to go from subtracting a portion of the gradient to adding the gradient. Okay, good. Okay, so what am I going to do next? I want to write this recursively. So let's take a look at where we are in our notation here. Good, so recursively, these are going to be the w's here, right? This is going to be wl plus 1 here. Taking the mapping from here to here. But notice that S1 on layer L plus 1 is going to depend on this variable, and then all of these are going to depend on this variable as I move in the other direction. Right? And so what we can do is we can write for an inner layer, right? We've got this for the outer layer, partial E partial SM script L is equal to the sum on the outside layer, j equals 1 to nl plus 1 of S. I want to write partial E partial SJL plus 1 times partial SJL plus 1 times partial SML. Good. Now, how does SML, or how is SJL plus 1 attached to, how is it using SML? Well, SJ on this outer layer, right, is equal to sigma, just like we did before, right? And the pre-state of that is just going to be our W. That's going to be the W that's attached between um, this mth node and the jth node. So do you remember how to write that? Yes, that's W JML plus 1 times our SML plus whatever else, right? And so how am I going to take this derivative then? Well, this is just going to be sigma prime of PML times RW JML plus 1, right? Which is the derivative of this with respect to SML. Good. So this is what that is. Let's see, do I have everything else computed now? I think so. Because these we're assuming have been computed, and therefore I can now compute this, right? And so therefore what we have just shown is that we can compute partial E partial W MNL, right? Using all of our notation. So I guess what I have not shown yet is that these are actually the deltas, although we did have a hint of that. Okay, so in the next video, the final video, we'll actually connect the deltas to the changes in our parameters. And also, we'll talk about how to compute the bias terms, bias corrections also. Alright, see you then.